Hey, it is 2 hours UTC, and therefore it is time again for Astronomy Daily Live. This is where a group of friends from around the planet get together every single day, gather in a circle, turn off the TV, forget about the news, forget about pretty much everything else except when it comes to astronomy. So that's what we're doing here. This is just a casual, fun, hopefully slightly educational uh, live stream show where we sit around and chat for an hour or so about astronomy, all things astronomy. Now, there's always things that I like to talk about, but uh, if anybody in the chat or anybody wants to post some kind of topic down down in the comments, I definitely read those and yeah, we can talk about pretty much anything. This is for new people. It's for um, the amateurs. It's for the pros. It's for everyone. Anybody that wants to talk astronomy, come on in and join this growing circle of friends. I've got 70 subscribers, and I get about that many views every single week, if not a little bit more. So that's not too bad. Um, uh, Definitely can be better. I like to get those numbers up if I can. But, even if I don't, I'm going to sit here and talk astronomy to the rest of the world because, you know, there are some, that um, aren't able to join the live stream, but you can watch later. So, hey, to all of you who are coming in later as well. So yeah, hope everybody's doing well. It was a pretty good day here. Yeah, it's definitely spring, and in fact, in fact, happy equinox. As of 16:15 UTC tomorrow, which is in about 14 hours from now, 14 hours and 12 minutes from now, it will be officially the vernal equinox. The vernal equinox, and that is when the sun crosses the celestial equator on its way north. So as of that moment, the declination of the sun will be positive and and moving even more positive. So yeah, it is the equinox. Yay! This is one of my um, favorite days of the year for sure. I sort of treat it like a holiday. Um, just you know, my own thing. Don't really necessarily do anything fun or exciting. Just mark the day. Just mark the day. So it is the equinox. Hey, that is awesome. That is very, very awesome. And yeah, let's see. I don't have any. I don't have any plans. Just gonna. Um, I'm gonna um, take the day from the normal um, day job, and I'm gonna sit at home and work. Just I actually did that today as well. So yeah, just starting the week off right and completely ignoring the beginning of this week. So cheers. Gonna get onto the chat here, onto the YouTube chat, and I'm gonna start up my live stream on my smartphone so I can sort of monitor progress there. Looks like it's running. Very cool. Yep, that looks like me. All right. So hope everybody's doing good. Yeah, we can do Q&A. We can talk telescopes. We can talk gear. We can talk cameras, different kinds of instrumentation. Um, we can talk um, reducing data. What do astronomers do? Uh, let's see. We can talk about uh, uh, dark sites, dark skies, bright skies, um, observing, observing planets, observing galaxies, uh, anything there. Um, we we can talk art, any kind of art that is either inspired by astronomy or created from um, 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 astronomical data. Uh, let's see, we can talk about particular papers that maybe we've seen, or some kind of a news item that we've seen. Sky is the limit, literally. So yeah, glad everybody could join in. Those of you who are joining in now or will join in the future, cheers. So I've got the standard hydrogen hydroxide tonight. Quite awesome. Usually quite awesome, and tonight is no exception. No exception whatsoever. So yeah, hope everybody's doing good. Yeah, I spent the day um, continuing to characterize my telescope and CCD system back on the evening of what mine was the evening of the 15th, uh, 4 nights ago now. I collected some calibration data, uh, and then did the live stream, and then I went back out and spent the next 3-ish or so hours uh, under a relatively dark, clear sky. The seeing, I think, was not quite as good as it could have been. It was sort of a hole between weather systems. So yeah, the seeing wasn't all that great. But yeah, I'm the one thing that I haven't really done with this scope yet is really, get into the nitty gritty in terms of operating it, in terms of collecting data, and then looking really, really, really hard at that data to see how good it can be. And there's sort of two things that I can do with this scope and the data I collect. The data I collect are just images uh, of the sky, very, very small pieces um, pieces of the sky. I My field of view is about 12 arc minutes by 8, so it's less less than 1/4 of the size of the full moon. So it's a very, very, very small portion of the sky. Uh, but in that field of view, at full resolution, I'm getting about 1 arc second per pixel. which is good enough for, or at least it should be, good enough for most things. So the two things that I can do uh, uh, right off the bat is um, um, astrometry, which is the measurement of, of the positions of things in that field of view, targets like either stars, asteroids, whatever is being observed. Um, so I can measure the positions of these things. The other thing I can do is measure the brightness of these things, and and uh, and so that is sort of what I'm in the process of um, determining is how well can I do astrometry and how well can I do photometry. And what I'm finding so far is with the astrometry, the measurement of the positions of things, that's relatively easy. Relatively easy. Um, I'm getting accuracies and precisions that are uh, subpixel, so less than an arc second. So what I can do is I can measure the pixel location of like a bunch of stars. So I've been looking at Messier um, 41, which is a open cluster in the constellation Canis Major, which is maybe about 3 or 4 degrees south of the star Sirius. So this is actually pretty awesome. Hey there, Tom. Pretty awesome cluster to view. You can definitely see it in binoculars through a telescope. It's great, and what it allows me to do in terms of trying, to evaluate this system is I can go to a star catalog like Gaia. I've been using Gaia, um, which has measured the positions of these stars, the right ascension and declination of these stars um, to very very high precision and as far as I know, good accuracy. So they are the measurements are um, accurate and very very precise. And so then what I can do is I can take my data, I can take my data and make the same kinds of um, measurements, right? I can measure the positions of each of the stars, and I can compare what I get to a catalog, to a trusted catalog like Gaia, and I can look at the differences between um, what Gaia says the position is and what I say the position is, and um, and I can do that for most of the stars in the field of view, and also several um, images. Cheers. And um, I can compare those two things multiple times, for multiple stars. And what I'm finding in terms of the astrometry, in terms of measuring positions, is that my accuracy is sub-pixel. It's about a third of 1 arc second. And my precision is actually about the same. It's about a third of an arc. second. So since my pixels are about 1 arcsecond in size, anything better than that, I'm pretty happy with. So the fact that I'm getting between a quarter and 1/3 of an arc second um, accuracy and precision in terms of the astrometry, I'm pretty happy with that. Pretty happy. So measuring the positions of things with this scope is very awesome. Now the photometry is uh, inherently much more difficult um, uh, for a number of reasons. Um, Again, I'm using Gaia as a standard, and what Gaia did is it measured the brightnesses of these stars as well, and it was also very broadband, basically covering the entire um, visible region of the spectrum. So from about 4,000 angstroms up to, well, I've got the plot here. Don't I still have the plot up? I thought I did. I thought I did. I thought I did. Yeah. So basically, from 4,000 angstroms to about 9,000 angstroms or so. So that covers the entire visible range of the spectrum. Uh, it's and I'm I'm basically doing exactly the same thing. I do have um, filters um, um, for this system, but in this case, I wasn't using it because I wanted to be able to compare to Gaia, and so Gaia, you have to assume, is a trusted source, and so you know the magnitude, the brightness of a target star uh, that Gaia sees is probably what it is. So if I'm seeing any kind of differences there, well, I've got to understand why. And so, cheers. So measuring the brightnesses of stars is much harder because you have a lot of well, you have a few at least systematic problems that you have to eliminate um, from your data first. There's primarily two. Sometimes you can say there's three, but there's primarily two, and that is well, there is a underlying uh, um, electronic bias that's usually very low level. Uh, but then there's a what's called a dark, and that is what's the best way to describe a dark? It's a um, it's it's sort of um, the um, the accumulated signal over a period of time, uh, but you're not measuring any kind of light. Uh, you're just measuring, sort of the dark um, current um, over a specified amount of time. It could be a second, it could be a couple of seconds, it could be 10 seconds or so. And it's basically just, the thermal noise. Yeah, it's a noise floor. And so that has to be dealt with. The the third thing is what's called a flat field, and a flat field um, is basically a measurement of gain, and there are sort of two sources of gain. Um, One is each pixel has a certain sensitivity, and you can set the gain on all the pixels to a certain value. Say a gain of 5. Say I'm just making up that number. Um, uh, so with a single dial, you sort of say, okay, I want all the pixels to have a gain of 5. But when you actually go in and measure um, the pixels, what the actual gain is, pixel to pixel, you'll see, 5.01, 5.03, 4.97, 4.9. Sometimes you'll turn the gain to 5, measure a pixel, and the gain will be 1,000. That is a hot pixel. Um, Something's wrong with it. Sometimes the gain will be 0. That means it's a dead pixel. So, all these things you have to take into account. The other source of gain is the optics themselves. The optical path is very, very rarely uh, clean or not obstructed by something, and that'll affect um, the gain of certain pixels. Depending on which pixel is seeing what portion um, of the optics, uh, that affects the gain also. So a flat field is is a is a light frame, is a regular exposure, but what the telescope and camera are looking at is effectively a, a, a gray flat field. It's not, there's no kinds of features, I'm not looking at the sky, right? So what I do in my case is right after sunset, uh, I'll already have the scope and computers and everything set up out there. Uh, right, maybe 5 or 10 minutes after sunset, the sky starts to, you know, go from a blue more to a gray, right? Um, a certain portion of the sky. If you've ever watched the sunsets, you'll you'll see that low down it's really really red, and then above the red is maybe a little bit of blue, and it gets darker darker darker. But there's a region um, sort of where it's not really blue anymore. It's not black yet. It's sort of a grayish color. So what I do is I take a couple of, and this is extremely sophisticated. Uh, hopefully this isn't going way over your head, because this is high tech stuff. Okay, this is high tech stuff. I take a couple of white T-shirts and I cover the front of the scope. I take the cover off, of course. I cover the front of the telescope, make sure the T-shirt material is nice and flat. I take a bungee cord and I wrap that around so it sort of holds the T-shirts in place. And then I point the telescope at this sort of gray portion of the sky, and I start taking exposures. And I have to set the exposure time pretty carefully, because what I want to do ideally, in the ideal situation, is that I want um, to take an exposure time such that uh, the maximum pixel value is about 2/3 of the brightest it can be. So in my case, this is a 16-bit camera, so the brightest a pixel will be is 65535. Um, so if I have any pixel that bright, then my exposure time is too long, and I have to lower it a little bit. So what I what I like to aim for is a maximum value, as I said, of about 2/3 of that, maybe around 40,000, 45,000 um, or so. And I want to try to maintain that if I can. Now, the problem with using the sunset is that, and I think that this uh, is right. Um, every minute, every minute, the sky gets about half as dark as it was. I think that's right. Maybe that's too fast, but I want to say that every minute the sky darkens by a factor of half. It's you know um, uh, each minute it's half as bright as what it was. So half. So you know I I need to take I like to take around 30 flat field images, um, and then I can combine those and get an average, and that you know that's just nice stats. Um, so in order to do that, that takes 5 or 10 minutes or so. Well, over the course of that time, the sky is getting darker and darker and darker and darker, right? And so what I have to do is what I found at least is that if I take 10 exposures at about 3 seconds, um, that gets me up to about 40,000 or so. And then after 10, it's dropped. It's dropped to maybe about 25,000. So what I do is I change the exposure time to 5 seconds, and that bumps me back up to about 40,000 again. And then I take another 10 of those. Uh, that drops me down again to about 25K. Then I do a series of 8-second exposures, which by then, 8 seconds usually isn't long enough, but I'm racing against time. So I have to compromise. You have to compromise. And so 8-second exposures, I'm starting around 30,000, and I get down to below 20,000 at the end of those 10 exposures. So that's how I'm taking my flat field. Now, I have to say, and I've been contemplating if I want to show the world my current flat field, because it is, I definitely have some cleaning that I have to do. My optical path is full of dust, full of dust. There is dust on the optics. Not quite sure exactly where. I have to get into it a little bit. I don't know if it's on the telescope itself or if it's on. Um, there's a window on the front of the CCD um, itself. Maybe there's some dirt on that, but what I'm seeing is a lot of what are called donuts. They're just out of focus pieces of dust somewhere in the optical path, and uh, that affects the gain. Now it's very subtle, right? I mean, it's at the 1 or 2% level in terms of gain. Um, and maybe it's a little bit more than that. 5%, 6% or so. I mean, I've got pretty flat fields, but if you scale things such that you only look at that region, then it's pretty obvious. But I should probably, for full disclosure, and to share with you the entire path that I'm going on here in terms of uh, hey there, Alex Bale. Nice to see you. I don't know if you're still there or not. You chimed in 15 minutes ago, so I'm not sure if you're here or not. But glad you stopped in and and yeah, made a flat Earth comment. um, so yeah, I should probably publish my current flat field just just for full disclosure and to let you, hey there, Uncle Bill, wave, 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 um, just so you can, watch my entire journey as I try, to characterize this beast for what will hopefully be a pretty interesting project. Uh, so so flat fielding is sort of a process. Now, the flat fields also have dark current in them, right? They have this accumulation of thermal electrons that have to be gotten rid of. So after I take my flat fields are number one priority, right? That's the most important thing. If you're not able to calibrate your data, you might as well not do it at all. You know, don't waste your time. Um, so flat fields and darks are extremely um, important, and flat fields have to be done every single time the system changes. So, for instance, if I were able to leave my camera on the scope, which maybe at some point I'll do that, but if I were able to do that, um, then I wouldn't have to take a flat field every single uh, um, time. Um, Flat field images as a filter? Mm, no, no, it's not really a filter. Flat fields are are um, um, measurements of gain, and that actually brings up an interesting point, Tom. Okay, um, if you are going to be using filters, if you're going to, not just have a wide open, um, full full bandwidth, full visible spectrum thing, um, you have to take flat fields for every filter. So, at least in my case, what I was doing last night was just completely wide open, no filters at all. Cheers. Um, so I just had to take one set of flat fields, and that was not filtered at all. But it's absolutely true. See, because another thing about CCD pixels is that they are wavelength. Their sensitivity is wavelength dependent. So um, so not only are they just brightness um, dependent, but uh, some pixels might be more sensitive to blue than they are to red. And so if you're going to be doing some kind of observing run that uses, 3 sets of filters, say either RGB or UBV or um, something else, then you have to take flat fields for every kind of filter, and and um, when you're using the sky uh, as your light source, the sunset sky as your light source, you have a limited amount of time. Now, in all of the major observatories, the way that they get away with this is that on the inside of the dome, they'll have this big, huge white screen, this big, huge white screen with lamps that throw full spectrum light on this screen, and then they point the telescope at this screen and they take their flat fields. And of course, they aren't limited in time, so uh, they can do that, pretty much any time that they want. And Uncle Bill, you bring up a good point about um, temperature. The temperature has to be stable. It has to be, set and then maintained. And so, my camera can do that. I set the temperature I want, the CCD to be at, and then I have to wait for that temperature to stabilize. That usually takes, 5 or 10 minutes or so. Um, and then it has to stay that way, the entire rest of the observing night, because yeah, that'll primarily affect your darks, because it's your darks that are measuring so the um, um, thermal electrons. Uh, so yeah. Um, but then, as I said, each of the flat fields, okay, um, have a dark current. So once your flat fields are done, you have to take darks for each of the exposure times of your flat fields. And that's exactly what you would do um, when you take your raw data. If you're doing 10-second exposures of some um, galaxy, then you have to remember to take some 10-second darks. And I usually like to take 20, 30 of those, and then make an average. That makes them a little less noisy. It also makes all the bad stuff um, um, pop out a lot more. And yeah, it's just um, good practice. So yeah, there's a lot that goes into uh, finally getting your calibrated data. So in order to do that, okay, first you have to make your master flats. So you have to take each of your flats and subtract your flat darks um, from those, and then combine those into what's called a master flat. Uh, since you're sitting on Peltier cooler, yeah, um, some kind of a what's it called? Um, 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 some kind of electrical cooler. Um, uh, yeah, I'm not exactly sure uh, what it is, but yeah, it does a good job. It keeps it nice and stable and nice and cold. And I can usually go. you know, 40 degrees below ambient Celsius. So don't necessarily like it to work that hard, but yes, it's a solid state. Yeah, yeah. It also has a fan on it too, so that air gets evacuated. I think it's a fan that blows out. Pretty sure. Um, so yeah, that um, warm air gets tossed out really fast. So so yeah, you create your master flats, and um, as I said, that's sort of a measurement of gain. So what you do after you create a master flat is you normalize it, and there's a number of ways to normalize it. You can take that master flat and um, um, make it such that all values go between 0 and 1. Uh, or, well, and that would be by um, um, computing the maximum pixel value of that flat and then dividing that flat by that number. Um, what I've done in this case is I've computed the mean value, the average value, and then I've divided my flat by that number. So I do have some pixels, that are slightly larger than 1, less than 1. It's that's sort of an arbitrary choice. I need to look at, you know, doing it a couple of different ways. I want to look at the max value. I want to look at the mean value. Um, Probably want to look at the median and the mode as well, and see how that goes. But since the flats are a measurement of gain, you want your gain to be between 0 and about 1 or so, because then what you do um, is you take your raw data of your target, be it a planet, be it stars, be it um, galaxies, whatever your target is, you subtract your dark field first, which is just a DC offset, right? It's just an offset. It's like a pedestal that your raw data sits on. So you subtract that off, joink, like that, and then you divide by your flat field because it's a measurement of gain, and gain is a multiplicative thing. So um, you subtract your dark field, and it goes junk like that, and then you divide by your flat field, and that sort of, you know, maybe you had a slope like like that, right? Because the pixels over on this side, for some reason, were more um, sensitive to light than the ones over here, right? So when you apply your flat field, it goes like that, flattens it out, which is what you want. So at that point, you've removed all of the systematic effects, and it's all you have left is two things. You have your sky background, and you have your actual target. So you still have to deal with sky and your um, target. So yeah, photometry, as I said, is much more difficult um, than astrometry. Um, the images have to be really terrible in order for the astrometry to be uh, really bad. But the photometry, it is hard. It is really hard. Um, because then you have to get into, okay, say that I want to measure, the brightness of a particular star, right? Well, do I, uh, you know, that star isn't usually going to fall on one pixel. It's going to fall on, some kind of an area, right? Uh, a number of pixels. Well, which pixels? How do I determine that? Do I draw like a circle around that and I add up all the values inside the circle? Do I make a box? Do I make a triangle? Do I make a hexagon? What kind of shape? And then how large of an area do I measure? I also have to take into account the sky, because the sky has a brightness too, sort of like the dark, um, except the sky actually has a brightness that needs to be removed from, say, the star that you're trying to measure. So how do I measure the brightness of the sky? Do I, uh, you know, make sure that I'm outside of a certain radius around the star, and I look at like a ring around that star, um, or in the case of like a box or a rectangle, and then how far out do I go? How many pixels do I sample? When I sample those pixels, do I compute the mean? Do I compute the mode? Do I compute the median? There, it's a tricky business. Um, uh, so yeah, you know, uh, there's a lot of variables involved and a lot of parameters that can be tweaked, and it's hurts the brain. Luckily enough, uh, I'm able to write all this code, um, so I've got complete control over the experiment. Um, the only thing that I don't know is what I don't know. So what I'm finding so far is that, uh, and this is very um, um, preliminary, is that my accuracy. So what I'm doing is I I don't have a way of measuring the actual magnitudes of these stars. I can't say, okay, that star there is magnitude 6.8, and that star there is magnitude 7. Okay, can't do that. But what I can do is I can measure the difference between them, the magnitude difference between them. So obviously, the magnitude difference between a 6.8 and a 7.0 is zero point 0.2 magnitudes. Okay, so I can go into Gaia, right? And Gaia has done um, these measurements for me and actually have actual magnitudes, right? So say that Gaia, uh, and in fact, why don't should I do that? Yeah, pictures are worth 1,000 words. So let me go over and share my screen. We're going to go over to my Discord server. Discord. Man, I wasn't going to talk about this the the entire time, but I've been working on this all day long, and I'm going to work on it all day tomorrow. It's yeah, sad but true. But this is what astronomers do. It's a lot of tedious, mind-numbing work. But yeah, let me just so I can show you some pictures. I like pictures. Dun, 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 dun. So a link to my Discord server is down. So if you want to join on in. Great to have you. Let's see. Where did I put that picture? Did I come down here? I don't know why it always does that. Hey, I don't know why I cannot simply scroll up. Thank you. Let's go up here, go up here, go up here. Don't I have a picture? Yeah. Okay. So, um, so let's just say that Gaia said, so this is just a raw image. So you can see a lot of bad columns, bad pixels. You can see that there's a slope here. This is reversed, so the bright stars are black. So you can see that it's brighter over here than it is over here. This is an uncalibrated image. I need to post a calibrated one of the same one, just so you guys can see um, what the differences are and how it cleans up beautifully. But let's just say that Gaia says that this is magnitude 6.8 and this one is magnitude 7. Okay, this one's slightly brighter than that one. Okay, then the difference between those two stars is zero point 0.2 magnitudes. Okay, well, that's what I can measure. I can measure differential magnitudes. So I can I can add up the number of pixel values. Zoom in a little bit. I can create some kind of radius around here and add up all the pixel values in here, and then I can take a sample of sky around it, and I can subtract the sky from that. So I just have the value of the star, and I can do exactly the same thing for this, right? I can measure all the values in here, and then I can sort of take a sample of the sky around here and subtract the sky off, and then I can measure the difference between this and this, and there's a very very simple formula to determine what the magnitude difference is between two things. It's just the ratio of the flux, the ratio of the fluxes. Um, you take the log base 10 of that, and then you multiply it by negative 2.5. And that gives you the difference in magnitudes between that star and that star. And I can look at that difference and I can compare it to what Gaia says the difference is. And that is a measure of my accuracy. Because if I'm really, really, really close to Gaia, then my accuracy is very, very, very good. And if I'm very, very far away from Gaia, say that I measured the difference here, and I'm getting like zero point 0.4. Okay, well, that's a difference of 0.2 magnitudes between what I'm measuring and what Gaia is saying, and that's not very accurate at all. But what I can also do then is I can take a number of these images, and in this case, I've got 20 of them, and I can measure the same two stars in each image, and say I get zero point 0.4 in the first one, 0.6 in the next one, 0.2 in the next one. Well, the precision there is terrible. So not only is the accuracy off, um, um, the precision is all all over the place. Precision is a measure of consistency. How consistent um, are my measurements? Uh, well, I can say that uh, my so far at least my accuracy isn't as good as I want it to be, and I'm trying to understand why. So, you know, if Gaia is saying, that there's a difference of like zero point 0.2, maybe I'm getting like 0.3 or 0.25. Um, uh, however, however, my consistency, my precision is actually pretty darn good. I'm getting I'm getting a precision of less than 1/10 of a magnitude. So I'm sort of thinking anything less than a tenth of a magnitude precision is probably good enough for what I want to do. If I can improve that, I definitely want to. And in fact, I haven't done the stats on the numbers that I've been working with today, but I think those are significantly less. So what I was getting as of last night was about 87 thousandth of a magnitude, like 0.087 magnitude precision. What I'm seeing now, just off the top of my head, I'm seeing about 30 or 40 thousandths of a magnitude, like 0.03 zero point zero 0.04 magnitudes in terms of precision. Now, as I said, my accuracy is still I'm not that's sort of where I am in terms of that. Um, some of the measurements are very accurate and very precise. Some of the measurements are not very accurate at all, but very precise. Most of the measurements, the precision is really really nice. It's the accuracy. It's being able to say that the difference between the brightness of that star and the brightness of that star is say zero point 0.2. I'm not getting zero point 0.2. I'm getting uh, you know um, off of that um, uh, by way too much of a factor, way too much of a factor. So it's 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 a difficult task. It's a difficult task for sure. Um, you know there there are complications. Um, for instance, okay, if I were to measure this star here, okay, measure the brightness of this star, and then I measured the sky, and it just so happened to include that little faint little star right there in my sky measurement, well, then I'm going to be subtracting too much from that. And so uh, I'm not going to get a good, accurate measurement of that guy. And so that's one of the things that I have to look at, and I'm not right now. Is that if my accuracy is leaning towards I'm I'm seeing things too bright or too faint. Um, right now, I'm I've the code I've got. I'm just measuring sort of the absolute value uh, of what the difference is, and probably what I should do is I should be looking at am I measuring too bright or too faint, because that might actually guide me in a direction. One of the things that I like to do, and I've done this um, my entire um, professional um, career is let the data tell me things. I've got to be open to that kind of a communication, but I like the data to sort of guide me and to show me what's going on. And so, yeah, one of the things that I definitely need to do is I look um, as I need to see whether um, I'm measuring too bright or too faint, um, and because yeah, that'll probably help uh, in determining which direction to actually go. Um, but yeah, it's a tough nut. It's a tough nut for sure. Now, when I say that my accuracy is not all that great, what I'm saying is that I'm I'm seeing um, differences between what, and it's sort of the differences between differences, right? Because I'm looking at the difference in magnitudes between two stars, and then I'm comparing that difference to the difference that Gaia says it is, and computing a new difference. Do you follow me? um, uh, and so those differences, I'm seeing. Sometimes I'm seeing like half a magnitude or so, and that is not that is not acceptable. Now, some of the differences are are very small, which means my accuracy is awesome. Less than a tenth. Um, but in a lot of cases, I'm seeing a third, a fourth, half a magnitude or so um, um, difference between what I'm measuring and what Gaia says, and that is unacceptable. But see, I have to assume, right? I have to assume that Gaia, that that those folks are doing it right, and that I'm doing it not right, or there's something else going on that I'm not aware. When I first noticed that there were differences in the accuracy, or that the accuracy wasn't um, um, what I'm able to tolerate. My first thought was, oh, well, I'm looking at the full spectrum, and Gaia is probably looking at a narrow band um, filter. They call it the G filter, and so I was like, okay, well, I need to find this out, because there are ways of at least trying to compensate for that. I found a paper that goes through the entire photometric process that Gaia used, and one of the plots that they have uh, is their sensitivity plot for this G magnitude. They call it a G magnitude, and it turns out that it is that covers the entire visible spectrum. So, I thought for a while that I was, doing a comparison between apples and oranges. Nope, it turns out that I'm comparing apples to apples. Probably, most likely, okay, most likely, um, uh, my sensitivity curve from my camera isn't exactly the sensitivity curve for Gaia's camera. But if that were the case, then I would see sort of a consistent accuracy difference, right? Um, all the accuracy, my measurements would all be off by, a tenth of a magnitude or half a magnitude. They'd all be there, right? But what I'm seeing is that some of the accuracies are just like spot on, right? I mean, my measurements are almost exactly what Guy is getting, and some of my measurements, as I said, are half a magnitude off, sometimes a magnitude off. Once they get more than about half a magnitude off, then my precision goes to hell too. So I'm just talking about the precise ones. So the precision of my measurements, uh, as I said, is really really good. I'm talking 50 thousandths of a magnitude, zero point zero 0.05 magnitudes. So the precision is right where I want it. Um, but the accuracy is all over the place. Some stars um, measure almost exactly what Gaia is saying, and some stars are, as I said, like half a magnitude off. So it's like WTF, what? So I'm trying to understand that. I am seeing, I'm getting good numbers down, down to about 13th magnitude or so. So that's not too bad. 14th magnitude in some um, cases. So that's for like a 2-second exposure. So that's not too bad. So yeah, I'm trying to understand. So as I said, I thought that maybe it was a case where I had apples, Gaia had oranges in terms of filters. That's not the case. So now what I'm trying, I'm maybe I'm seeing variable stars. Maybe I'm seeing variable stars. I don't know. Um, I've spent most of today, sort of looking really, really hard at how I'm counting up these pixels, making sure that I'm getting them all, making sure that the sky is right, you know, all of that. Um, but now I need to start, picking on the individuals. I need to say, okay, why why are why is this star half a magnitude off from you know what Gaia says? And maybe I'll get an answer. Hopefully, I will get an answer to that. It's a it's a tough nut. It's a difficult process, but it's very very awesome, very very fun, and wouldn't have it any other way. Especially because if I'm able to actually do this, uh, the results are going to be extremely interesting and extremely exciting. So we will see. Time will tell. But hey, I have gone over my hour, and I definitely respect your time. I'm glad that you're coming in and you're spending some time in the circle of friends talking astronomy. We did uh, 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 some telescope stuff tonight, so that's always fun. This is just uh, on the top of my head, so that's what comes barreling out. Um, so hopefully that was moderately interesting and fun. As I said, I will keep you apprised of this project. I definitely want to take you all along um, on it because well, it's educational too, and I hope you get something out of it at least. I know I do. It's often useful to sort of talk through problems. What I actually end up doing is pace. I will pace. I will get up and I will just wander wander around, wander around, wander around, and uh, yeah, just think about the problem. Think about different things that I can do to deal with it. Maybe even solve it. Who knows? It's fun. It's interesting, and you know, um, uh, although it's all electronics and not necessarily high tech stuff, but relatively high tech stuff. I really feel as though I'm you know peering into the eyes of nature, and as I said, I let nature, I let the data sort of guide me, especially if I'm lost. It's like I don't. I mean, and that's sort of where I am at the moment. I'm not exactly sure why. In some cases, I'm getting measurements that are like dead on, spot on, um, and you know repeatable, right? And in some cases, I'm getting really good um, repeatability, but I'm like way 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 off. So mm, I'll continue to let it cook. I definitely um, this is how and why astronomers can spend years looking at one set of data, because it's a minefield. It's a minefield. All right, I'm going to get out of here for now. I've had way too much fun today, and I need to have a little bit more fun before I call it a day. um, yeah, I'll keep you apprised on all that. I'll I will post an image of my flat field as it is right now. Don't don't laugh at me. Please don't judge. It's but actually, it's pretty typical. It's a pretty typical flat field. Um, I've seen much better, and I've seen much worse. So at all levels. So yeah, if you've never seen a flat field before, maybe you'll get a little bit of a surprise, because it's like if you've never seen one, then it's like nothing you've ever seen before. Um, so yeah, yeah, I will post a picture of my current master flat, just so you can point to it and laugh, and see what astronomers have to deal with, the crap that they have to deal with in order to get these measurements. It's insanity. It's total insanity, but it's very very fun and very very satisfying. Keeps me out of trouble if nothing else. So all right, I'm going to get out of here for now. Thanks for hanging in, and Astronomy Daily Live will return tomorrow. It's so far I've noticed that tomorrow has arrived, and so I can say this with pretty good confidence that tomorrow will be another live stream, 2 hours UTC. Share this with your friends. If you haven't subscribed yet, make sure to subscribe. I want to build this um, community up a little bit. And yeah, how do I do that? I don't know. I think I'm just going to keep doing what I'm doing, talking astronomy, having fun, you know, relaxing, having a chill time, consuming beverages of choice. All right, I'm going to get out of here for now. Thanks for tuning in, hanging out for a little while. I will see you on the spin. All right. Have a good day. Good night. See you in less than 23 hours. Peace.